In lesson 6, we're going to be looking at scaling solids and seeing how surface area and volume changes when we are dilating figures. So in this first activity on page 242, let's just find the volume of each cube and let's do it mentally. So try to do it without a calculator, write an expression or the full volume. The volume formula for a cube is the side cubed, or length times width times height. So go ahead and figure out the volume of these 4 cubes. So for this first one, volume, so we would say volume equals 2 cubed, or 2 times 2 times 2, which is 8. And then meters cubed. Volume for this next one would be 5 times 5 times 5, or 5 cubed, which is 125 feet cubed. Third one, 1 cubed, so 1 times 1 times 1, or 1 centimeter cubed. Fourth one, 1/2 cubed. So for simplifying this one, you could write out 3 1/2s times each other. So then tops times tops, 1 times 1 times 1 would give you 1, 2 times 2 times 2 would give you 8 inches cubed. You could also use a rule of exponents that you can bring this cubed into both the top and the bottom. Because you see here you did 1 times 1 times 1, so you got 1 cubed, 2 times 2 times 2, so you got 2 cubed. 1 cubed is 1, 2 cubed is 8. All right, then if you're in class, then you're going to be working with these things called unit cubes, so just little blocks, and we're going to be building different shapes. So taking a look here, if we're looking at the surface area and volume of unit cubes, so if we kind of I just drew an example here. You could build this with your cubes. This one, the base of this structure has 5 cubes, okay, and then it's 2 cubes tall. So if we were looking at the surface area here, so you'd be counting the number of cubes on each surface. So this surface here has 2 cubes, and then remember there's that same exact surface back here. Okay, so for those surfaces, we end up with 2 on each one, and there's 2 of them. So that's 4. For this front panel, there's 10 boxes here, and then there's another one in the back as well. So we've got 2 of these with 10 boxes. And then the top has 5, and then there'd be another one under here, okay, the bottom. So we'd have 2 of these with 5. Then you could just total those up, and that would be the surface area. So when we're looking for surface area, we're counting the boxes along the sides. So 10, 20, 34 for the surface area for this example, and then units squared. Then volume, it's how many actual cubes make up the structure. So we've got 5 cubes on the bottom, 5 cubes on the top. So the volume here is 10 units cubed, okay, or 10 of those 1 by 1 cubes, 1 by 1 by 1 cubes. So that's what we're talking about for surface area versus volume. So let's go ahead and look at 1 cube, and then let's start dilating it. So if we had 1 unit cube, so here's our 1 unit cubed, and then we're going to dilate by these different scale factors. So if we're going to dilate this by a scale factor of 2, we're going to extend not only the width, okay, not only the length, but also the height. So you're dilating all 3 of these measures. So this would be a dilation of 2 on this unit cube. So now we see that we've got, instead of 1 by 1 by 1, now we've got 2 by 2 by 2. And then you want to come up with the surface area and volume of each of those structures. So let's take a look at the scale factor the original one. Okay, so here's our 1 unit cube. So what's the surface area? So remember, count all the surfaces. So we've got this front one and the back one. So that's 1, 2, this one and this one. So 3, 4, and then 5, 6. So there's 6 units squared, okay, on one of these cubes. And then the volume would be 1 because it's 1 cube. So now when we've dilated it in with 2 by a scale factor of 2, so now this surface on the top is 1, 2, 3, 4. And then remember, there's the same one on the bottom. Okay, and then this front panel is 4. There's a back panel here of 4. This panel has 4 squares on it. So does this back one. So we've got 6 surfaces, all with 4. Okay, front, back, top, bottom, left, right. So count those all up, and that would be 24 units squared. And then how many boxes do we have? How many cubes did it actually take to make this structure? So we see that we've got 4 cubes to get kind of this top. Okay, so you see 1 cube, 2 cubes, 3 cubes, 4 cubes. And then same for that bottom panel. So there's another 4 cubes. So it took 8 cubes to make that one. So now go ahead and do a scale factor of 3. So you're going to do, triple each of these lengths. So you're going to have 3 boxes by 3 boxes by 3 boxes. And then do it for 4, count up the surface area and the volume, and complete that table. Then come back to the video. So in those structures, when you counted them up, so you should have seen a surface area like we did together, 6 and a volume of 1 for the 1 by 1 by 1 cube. For the 2 by 2 by 2, you got 24 for the surface area, 8 for the volume. When you did a scale factor of 3, you got 54 for surface area, 27 cubes it took. Okay, and we could put in units squared for each of these. And then units cubed. So then for that fourth one, or for a scale factor of 4, then you're getting 96 for the surface area and 64 for the volume. So now go ahead and take a look and see if you can come up with an expression for the surface area. Okay, can you see a pattern that's happening here? And write in the expression. And then can you see a pattern for the volume? And try to compare it to the scale factor. Okay, so try to compare it to the scale factor, thinking of if you could just call the scale factor K, how would you get this one? How would you get this one? So we notice that this first one, okay, our scale factor is 1, and then this is 6. Okay, so it's 6 times bigger here. And then when we look this way, okay, we had 6 surfaces. We still had 6 surfaces, but it was 4 times bigger. So 6 times 4 gave us 24. So we kind of see like some of that happening. So in this one, kind of you just have 6K. This one looks like the 4 is this number. Okay, so for our scale factor, but K squared, which makes sense when we're using area. So actually this one is squared too, because 1 times 1 is still 1. So then let's see if that works for this one. So 6 times 3 squared, which is 9. 6 times 9 is 54. And then 6 times 16 here, which is your K squared, gives you that 96. So 6K squared appears to be the pattern there. And then how is this one going to volume? So this looks like it's just 1. 8, if we try to get that as a 2, we saw in our warm-up that that was 2 cubed. And 1 cubed would just be 1. So let's check out here, is 27 3 cubed? And it is. 3 times 3 is 9 times 3 is 27. 4 cubed, 4 times 4 is 16 times 4 is 64. So seeing a k cubed here. So comparing both of these expressions, compare and contrast the surface area versus the volume. And so both expressions look like they deal with the scale factor k, but area, it's a k squared, and volume, it's a k cubed. And then we do also see that 6, okay, which has to do with the number of surfaces. So a cube has 6 surfaces. So when we're using surface area, we've got the 6 surfaces times the scale factor. All right, which is then what this first discussion talks about on this slide. So that 6 represents the number of surfaces. And so why does the k cubed not have a coefficient? And really it does. There's just a 1 in front of here. Because that first cube, it was only 1 cube. So we had 1 cube versus the first surface area. There's 6 surfaces. And then how does the work with area in 2 dimensions relate to this work with surface area in 3 dimensions? So you still are getting that k squared, but now there's a bunch of different surfaces. So you're not working with just one 2-dimensional shape, but you are just working with 2D surfaces on the 3-dimensional figure. So you're still getting that k squared because you're still just doing 2 dimensions. Okay, so that's where these are related. K squared because you have a length and a width. Now when you look at volume, okay, so the k cubed adds in a dimension of a height. So now not only do we have length and width, we're also adding in that 3rd dimension of height. All right, then let's take a look at 6.3 starts on page 244. So Claire says, we know that if we dilate a cube by a scale factor of k, the cube's volume is multiplied by k cubed. It seems like that must apply to all solids, but I'm not sure how to prove it. So Elena says, earlier in the unit, we showed that we could cover any 2-dimensional shape with rectangles. So the property that area changes by k squared when we dilate a figure by k applied to all shapes. So if you remember back to that blob, not just rectangles. Can we do a similar thing here? So using Elena's line of reasoning, can we argue that for any solid, it could be a with a dilation of a scale factor of k, that it would be k cubed? So similarly, you should be able to fit little cubes, okay, into any structure, and you can just fit to estimate the volume. Just putting smaller and smaller cubes into there should be able to fit into that volume and give you an estimate. So it would make sense then that k cubed would impact any shape, not just cubes. So suppose a triangular prism has a surface area of 84 centimeters squared. So this has a surface area of 84 centimeters squared. So all of these surfaces total 84. And a volume of 36 centimeters cubed. The prism is then dilated by a scale factor of 4. So your k value is 4. Calculate the surface area and volume of the dilated prism. So we know that each of the lengths is multiplied by k to get these new ones. So what would we do for surface area? So surface area is impacted by k squared. So we would multiply these by k squared. Volume is multiplied by k cubed. So we would multiply the 36 by k cubed. So for the new surface area of this dilated shape, we would do 84 times 4 squared, which is 84 times 16. And so 84 times 16 tells us that the surface area of this dilated shape is going to be 1,344 centimeters squared. The new volume, so we would do volume equals 36 times k cubed, so times 4 cubed, 4 cubed being 64. So we would do 36 times 64. So our new volume for this dilated figure is 2,304 centimeters cubed. So surface area multiplying by k squared, volume multiplying by k cubed. All right, so we learned that if we dilate a rectangular pyramid by a scale factor of 5, okay, so any shape by a scale factor of 5, how do the side lengths change? Okay, so for side lengths, when you're dilating, they just multiply by k, or in this case, 5. So just multiplying side lengths by 5. How does that change the surface area? So surface area, because it's an area, multiplies by the scale factor squared, so 5 squared. Volume would multiply by the scale factor cubed. So this one would multiply by 5 for any side length. Okay, area would multiply by 5 squared, or 25. And volume would multiply by 5 cubed, or 125. So what are some situations where a solid is filled with something different than its surface material? So different than what it's made of, and what makes up the interior and the surface in these situations. So if you can think of some. And so, a bunch of different things like this. So a pop can is filled with soda instead of aluminum. So the surface, so your surface in this would be the aluminum. Okay, and then the volume would be the soda. Can't really see that I wrote that, but so the volume in that case is the soda, how much it fills. The Cheerios box is the cardboard is the surface. The Cheerios are the volume. Okay, or your surface on a glass or a bowl is the glass, and then the liquid that fills it. The bag for chips is your surface. Okay, so that foil, and then the chips are the volume. You can put this on your reference chart. So this is the big things that we learned. So when we've got scale factor of volume, okay, so volume is by k cubed. You can also write in that the lengths are by k and the area is by k squared. And we can see that in here. So if you just multiply a length, right, there's just this 1 k value difference, just k times that length. Now if we get into area and you're multiplying these, now you've got 2 k's, so area is going to be a k squared difference. And then when we add in that depth to get the volume, now you add in a third k. So k for the lengths, k squared for area, k cubed for volume. Lesson summary here. So area of an original shape is multiplied by the square of the scale factor. So that's that k squared. So if we looked at a specific example here, so you've got all these lengths. So if it's scaled by a factor of 3, these lengths would all multiply by 3. Okay, so 5 times 3, 4 times 3, 3 times 3. Any of the surfaces, so the area of this front panel here is 12, because it's, or sorry, this side panel. So I have that labeled wrong on here. So this should really be 20. So this should really be 20 because it's the 4 times 5. So that's going to be multiplied by a scale factor of 3 squared. Okay, so when we multiply this one to get our new area, it's going to multiply by 12, or sorry, by 3 squared. And it's going to be 20 times 3 squared. So that's going to give you 180 for that new area. And then volume is length times width times height. So multiplying all of these. So the volume of this smaller one is 60. So we would multiply that by 3 cubed to get our new volume. So multiplying by the k cubed value. So then this just talks about that. So if the original was 60, multiplying by 3, like you could multiply all of these, the lengths by 3 to get the new volume. You could also multiply by 27, which is your k cubed. So surface area is changed by the square of the scale factor, and volume is changed by k cubed.